much, Mark. Great. Thank you. So, next speaker is Abbos Shodiev. So, who is a third-year PhD, so working in artistic projects. So he's doing a lot of stuff. I mean, he worked a lot on impedance simulations, 3D resolve impedance simulations. So this is something that he showed in the previous webinar series in last year. And last year, so he worked a lot on the simulation of electrolyte infiltration on porous electrodes, so in particular using the Lattice-Boltzmann modeling method. So Abbos, the floor is yours.
Thank you very much, Alejandro, for kind introduction. Hello, I'm Abbos Shodiev, third-year PhD student within artistic project, as Alejandro mentioned, and part of my work is devoted to create digital twin of electrolyte infiltration step in the manufacturing of lithium-ion batteries. So today's my talk will be devoted to this. Here, typical battery fabrication process, step by step shown. I will not repeat Alejandro and Mark, so I think everything is clear. It's just important thing is that electrolyte impregnation step takes part between formation step and after calendaring step. So now let's go through the outline of my today's topic. First, I will go a bit about electrolyte infiltration, what is the state of the art and what people are doing as far as I know. And then I will talk about the model I created within project to describe this infiltration step. I will give some simulation and results as well, just to show you that what it can be done with the model. Because as all of you know, it will be free to use on artistic website. So it's just a bit representation of some results. And at the end, I will finish with small perspectives, my presentation. So basically, like when I started my PhD 3 years ago, there was not too much studies on electrolyte infiltration step, and probably up to 5 publications. That's it. But recently, really, like last 3 years, number of publications in the electrolyte infiltration step increased. Of course, it's because of a lot of increase of number of factories to produce batteries, but as well there is some requirement policies included in safety. Before it didn't exist. Some new it now includes new regulations such as in European Union. This is like amount of free liquid electrolyte is now limited to very small number, and as you can see here from numbers, like most of the produced battery cells had excess electrolyte inside. But in the European Union, they are limiting to this kind of excess amount of electrolyte within the cell due to the safety concerns. So, as I said, during the last 3 years, number of publications increased a lot. But the thing is that they were all of them working independently. So you can imagine some work in North America, in Europe, and especially in like China and Korea and in Japan. And all of them were independently working without knowing each other. And each of the groups kind of suggested new kind of technique to analyze electrolyte infiltration step. For example, one of them is neutron radiography based visualization, and other one like X-ray based visualization. So as you can see, they can have a pretty clear idea about how electrolyte is penetrating and how it's going on. But on the other side, there is like a time step, if you can see, between imaging is quite big for electrolyte flow, especially. Further in the results, you will see that initial part of the electrolyte infiltration is very, very important. And then some other people also doing, people like becoming very creative. So they are doing like a glass, they are putting in glass in two offside and putting self-standing electrode in between, putting drop by drop and taking an image how electrolyte spreading here. So for example, A here shows for graphite electrode and B shows for NMC electrode. As you can see, spreading speed and spreading shape is not the same at all. As far as we know, like because graphite has more porosity with bigger pore size distribution compared to NMC electrodes they tested. But still here, as you can see, timing is a quite big time step for this kind of liquid penetration Recently, last year, 2 papers published on the new way of measuring the electrolyte infiltration, which is using ultrasonic scanning. So they can be, actually, this is quite good technique, quite accurate. And this also can be included during the manufacturing step. And the authors suggest that it can be inside the chain of line before formation step include to be sure that electrolyte is homogeneously distributed and we don't have excess amount of electrolyte. Other groups also did use different, not visualization, but electrochemical kind of tests to understand the electrolyte weighting step inside the electrode. For example, using impedance spectroscopy. As you know, like if you have a small amount of electrolyte, for ions it's hard to move, so overall resistance is higher. By time goes on, that they put more and more electrolyte and measures the impedance overall. As you can see, overall impedance is decreasing, which is overall ionic resistance is decreasing. Therefore, they are concluding like how electrolyte is going through the cell, basically, it's the rate. This one is particularly, second work is quite interesting. I find out that they try to combine measurement of the electrolyte infiltration degree with some after with the first cycling step. So when you have a lot of electrolyte, first after wetting, you put your apply current and you measure the potential. So ACI formation takes part, right? But then what they're doing, they're applying current, measuring potential, but different degree of electrolyte, different form of ACI growth. From this, of course, the applied current and potential difference changes accordingly. And from here, they try to measure the electrolyte wetting degree. But still here, a lot of work must be done because of during ACA formation, we know that's not only amount of electrolyte increasing, but lot of other things are going on, which changes the voltage overall. So if maybe a lot of data is generated by this technique, it can be quite useful statistically, just find out the impact parameter and then maybe can be used. But in our group, as you know, we are more theoretically work we do, and we theoretically try to understand, of course, combine it with always with experiments. Then we wanted to do simulation of electrolyte impregnation by using fluid dynamics. There are several options you can do, like using computational fluid dynamics, like a finite element method, finite volume method, or let's say molecular dynamics if we have a super access to the big computational computers with a big computational ability. So computational fluid dynamics, in one of questions were asked like why FEM and FEM cannot be compared to the lattice-Boltzmann. What is the advantage of lattice-Boltzmann? The thing is that there is no advantage except the simulation rate, because when you have a computational fluid dynamics, you have to mesh your electrode, and of course more and more precise you become, because inside the electrolyte infiltration, as Alejandro said, contact angle matters, which is just surface of the electrode and electrolyte, and then also bulk. So very fine mesh requires, and it of course takes a lot of computational power. And also molecular dynamics, as you can say, it's not possible in the battery level or cell scale even. It's very small dynamics, unless you don't have a huge computer power. So in this sense, after scanning a lot of different tools, we come up in our group that lattice-Boltzmann method is the best tool, because first of all, it's like you can divide into lattices accordingly as you want, accuracy. And so what is lattice-Boltzmann method, roughly speaking, is you can imagine molecular dynamics where molecules move around space, accordingly force interaction in between. In the lattice-Boltzmann, what we do is just we divide into lattices, small lattices, and inside we fix the direction of particles and distributions there. So therefore, we somehow simplify molecular dynamics, but still it's quite close for mesoscale simulations. One of the advantages of lattice-Boltzmann compared to the FEM or FEM simulation is that it's very highly parallelizable. So computationally, some studies compare these two tools, and it's like it can run like up to 100 times faster than FEM or FEM tools. So therefore, we decided to choose lattice-Boltzmann method. Now let's talk a bit about physics without equations, just to explain roughly what's going on. So we have what we have in your, we have electrolyte with higher density, and we have a gas inside, which is also fluid in fluid dynamics term. And when you have a gravity here applies, what happens? Your higher fluid with higher density goes down, and higher fluid goes up. Lower density fluid with lower density goes up. Right? This is typically very common equation. The second thing, what goes on, we have some particles and applied pressure or applied gravity, which allows move fluid. And then through the particles it goes through, we need Navier-Stokes equations. And the last part of the puzzle is contact angle, because we have two fluids, fluid or gas, let's say, and then solid. And then accordingly, we take into account contact angle. So these three models were developed separately. Then we combine it into one and move to the 3D representation. We replaced simple particles with our electrodes, and this is what we get at the end. So it's like a 3D view of electrolyte infiltration. Electrolyte is here in red color, and this is cut view of the electrode. I'm showing you electrode with CGMD, coarse-grained molecular dynamics, because you already know from Alejandro's presentation that what coarse-grained molecular dynamics what kind of electrode it can generate. Here, as you can see here, some small air-trapped regions because of pore blocked, or sometimes air also drops not because of clogged pores, but when you drink a water, if you pay attention in your glass, there is a water and some bubble because of the strength between fluids. So this kind of 2 or 3 different kind of bubbles can stay within the cell. And of course, it will influence overall electrochemical behavior of the cell. So I will show more quantified number for this at the end of my slides. So now after developing the 3D lattice-Boltzmann model, the idea was behind, okay, first we go through the different electrolytes, or we can go through different electrode structure. So when we have a 3D electrodes and we're already in 3D level, it's of course, we went through first to check the different mesostructures or microstructures for these electrodes. Source of electrodes, we choose differently, as diverse as we can, coarse-grained molecular dynamics. We obtained by tomography some electrodes, and we can generate stochastic electrodes as well. And we used some application like a geodic to diversely get different source of electrodes. Then these electrodes were segmented by Inov, which maybe Shushan will talk about this application. And then we imported these structures into electrolyte wetting simulations, which is lattice-Boltzmann models. Further, after simulation is done, we did several kind of characterization of such as saturation curves, pore size wetting analysis, or electrochemical characteristics. Saturation curves basically say saturation versus time. Saturation means how much amount of volume occupied by electrolyte. And then we could get, as it was 3D structure, we could get a realistic images of the pores inside. And then we did some characterization how pores influence as well as overall saturation time. Then we do electrochemical characterization at the end to see the influence of the wetting degree. The first thing we did, just to see, simplest thing you can do is different porosities, right? You generate electrodes with different porosities, keeping the same ratio of active material, binder, carbon black, keeping everything the same, just controlling the porosity. As expected here, higher the porosity, saturation goes close to the 100%, and it feels quite fast. By decreasing this porosity of the electrolyte saturation slope goes even lower, and it goes slower, and it doesn't reach the 100%. Now in our model, we can also look at the rate of the electrolyte within the structure, average rate. As you can see here, this represents the rate, and this is by time step, how it goes through the structure. Higher the porosity, higher the rate or velocity of the fluid within the structure, and it goes down because, of course, it's finished, right? And the structure reaches 100% here, so that's why velocity goes down, all of them almost. And then accordingly, it goes straight forward this way. Most of people might think this is quite evident, but of course, when you show the model, you want to represent it that people find it useful. You want to start with the basic things to show that model is capable to capture this kind of parameters. Further, as I mentioned before, we had a tomography electrode. We have a electrode structure obtained by tomography, and we have uncalendared NMC electrode and calendared NMC electrode. Of course, after calendering, you decrease the porosity, but not only porosity, you change pore size distribution as well. Now we can study not only how porosity affects, but pore size distribution within structures changes. Here, these two kind of structures you can see uncalendared versus calendared electrolytes. So porosity, pore size distribution, of course, plays role how fast electrolyte penetrates within the structure. And then calendering, of course, leads to the decrease of electrolyte flow rate. Here I represent the saturation curve for those two electrodes, calendared versus uncalendared. And uncalendared tomography electrode with higher pore size distribution and higher porosity, as expected, has higher saturation rate, and its velocity starts higher and goes sharp down. On the other side, calendared tomography, as expected, saturation takes like 3 times more time, and it doesn't reach 100%, and velocity goes slowly down. So this is the captures of several time steps, snapshots of several time steps in the electrolyte infiltration step. So on the top, uncalendared, and here calendared electrodes. You can see here electrolyte is penetrating homogeneously. On the other side, for calendared one, it's entering inhomogeneously. And at the end, it feels much more faster than, of course, as shown with saturation curve. The same story goes to when the gas leaves the cell, leaves the electrode. So you can see here, like for uncalendared one, gas leaves homogeneously, and it has less air trapped within the structure compared to the calendared electrodes. Now let's look at the pore network of the electrodes, so we can extract pore networks as well. The question was here, how pore size influences the wetting degree of the electrode and wetting rate. Therefore, we extracted the pore network, and we listed all the pores by size, and we divide into them 3 groups. First 33% is big pores, second 33% is medium pores, third last 33% is small pores. The same for this electrode. But here it doesn't mean this big pore size equal to these big pores. It's just we arbitrarily choose like this, divide into 3 groups. If you not agree with this, you can choose other ways, methods, like accordingly divide by pore size distribution graph. What is big pore, medium, and small pores, right? We can see here that big pores in both cases reach 100%, and as well they go very fast compared to the other 2 groups. But at the same time, in calendar tomography, you can see like a difference is become bigger, but medium and small pores has almost the same. It is because of, first of all, pore size distribution was very small and narrow, and then difference between groups becomes smaller. But here you can see perfectly that higher the pore size, higher the saturation. Here they might change alternative bit. This is here like it becomes of pore, depends on pore network as well. For example, after some length of the structure, big pores are connected through medium and small pores. This is the rate accordingly with the pores, like big, medium, and small pores, and big, medium, small pores. As you can see here, like higher the pore size, higher the rate, and faster it fills. And as well, medium pores goes next, and then small pores for the both electrodes. Further, what we did was we had graphite electrode, we had separator tomography, we had NMC. So what we decided, like let's say how wetting will influenced by when electrolyte comes from NMC side, of how it influenced by if it comes from graphite side. And do they have the same overall saturation number? For example, here, so graphite, we have 31% porosity, CellGuard 55%, separator, and uncalendared tomography NMC electrode 48% of porosity. So here again, I present saturation curve, as you can see, because NMC had higher porosity in the inlet, so it influences, like it goes overall faster. Initially, it starts higher and goes faster. Compared to the graphite and CellGuard, which had the lower porosity, and it goes slower compared to the first cell. But here you can see the steps, which means like electrolyte is coming from one structure to the another one, like entering to the separator and etc. to the NMC structure. Here is again, I show the velocities, and we can see like how velocities change across peaks. You can see here, like when the fluid enters to the new structure, part of new structure, like NMC, separator, or graphite. Now I will go back to this graphical representation of electrolyte wetting, post-electrolyte wetting simulation. So this is when we do models, usually we expect that electrolyte occupies 100% of the space and then ions free to move. But now in reality, we know that saturation degree is not 100%. We have locations with air trapped inside. So electrolyte cannot go through, so they should take a longer path and tortuosity numbers, right? In order to do so, we do electrochemical impedance spectroscopy model in symmetric cells and discharge. What is electrochemical impedance spectroscopy in symmetric cell, which I presented last year? Basically, we have the same electrode on both sides in between separator, and then we replace electrolyte with a diluted one and replace the salt lithium with TBA chloride, basically in order to make it blocking conditions. So there is only migration takes part and double layer formation. Initial this point, as we know, it's coming from electronic resistance, and then we know that electronic resistance didn't change for the electrode. But through the 45-degree slope, we can see how migration takes longer. This one with the assumption 100% filled with electrolyte. The red line shows here post LBM simulation with some air trapped inside. And you can see here ionic resistance is around 20% higher, and tortuosity becomes also quite a bit bigger compared to the with assumptions that 100% filled with electrolyte. Further to do so, we did a discharge model to run to see how this affects overall the capacity we get at 3 C rate. So peak is quite high because we should go to the little bit high C rate in order to see effect of ionic resistance. So as you can see here, 100% filled with electrolyte assumption shows more capacity than the actual capacity. So there is like we should be quite careful when we do these kind of assumptions inside the models. Of course, we cannot avoid some assumptions in the model, and for simplicity, we always assume 100% filled with electrolyte. But still, it's not negligible. And I think this can be even bigger for the solid-state electrolyte-based cells, because we know that contact resistance is one of the biggest problems there, as far as I know. So it's not negligible, let's say, when we simulate. So it should be taken into account. What is the take-home message? So this model is fully developed, it's ready to use, and it's integrated with the artistic simulation workflow of the manufacturing process. So it will be combined, and I believe next year it will be already available for the public. And it was used to characterize different electrode structures. What is the perspectives? Now we have a model here, because when electrolyte goes inside the cell or inside the battery, we know that electrodes swell, especially binder inside. So now we developed electrode swelling after contact with the electrolyte. So this work will come up soon. Also, we are doing a systematic study for different electrolytes and cell formats to understand what cell format, what kind of cell format is better for electrolyte infiltration step in certain conditions. And we are just scanning different electrolytes with different parameters to optimize or to understand which electrolytes takes how long time for penetration. So as you know, this lattice Boltzmann model, from beginning I was telling it's time consuming. It like simulations can up to from 1 day to 20 days, depending on your size and depending on your lattice. But advantage is that it gives a lot of huge data. And then you can run a lot of simulations if you have computational power. So you have a lot of data. Then I was talking within group, guys, like we should improve this and make it faster so we will be able to scan it very fast. So this kind of work was performed based on machine learning to accelerate the simulation. So on Thursday, Oyer will speak briefly about our work regarding machine learning algorithms. That's all from my side. Thank you very much for your attention. And if you have any questions, I will be glad to answer.
Thank you very much, Abbos. So nice presentation. So this is basically the idea of this machine learning model is to replace lattice Boltzmann, right? So the idea is instead of using the lattice Boltzmann simulation of the electrolyte infiltration, so using machine learning to predict the way that the electrolyte penetrates in the electrode, which is much faster. In few seconds, you can get the results, right? That instead of waiting several days as you used to do with lattice Boltzmann method. Yeah. So we just have a bit of problem with your camera, Abbos. I think we don't see you very well.
Oh, I don't know. Usually when I test, I don't know.
Maybe you have a lot of applications open. Hi, Shirley. We can see Shirley in the screen. Nice to see you. So, Fernando, do we have questions for Abbos?
Let's see. Yes, here we have a question from Alexis Laforge, who asks, electrolyte infiltration machines usually apply a certain level of vacuum. Would you be able to investigate the effect of pressure level on the infiltration efficiency, rate, and filling level? This would definitely have a practical interest for manufacturers.
Thank you very much, Alexis, for this question. It's quite it's a very important question because we know in electrolyte infiltration step, first we do vacuum, and then inside the vacuum, electrolyte goes in through. So here, model I presented that gas inside already, then it goes out through to the applied force, and then electrolytes takes part, right? But this simulation easily can be divided into two steps. You just apply the force or vacuum, just air inside, then you let it, whatever air stays inside. Then you take out the applied force and just put the electrolyte inside, and then electrolyte goes in due to the vacuum soaks in. So this model can be just easily divided into two simulations to represent this step.
Thank you for your answer, Abbos. So one question from my side, since, you have these wonderful simulations, right? And the whole idea is, in a way, training, a machine learning model to try to speed up this whole thing. Could you maybe comment a little bit on how many parameters you would have in your parameter space? Do you think your simulations cover all that you're interested in terms of modeling the full phenomena here, or you think you will need always more simulations to actually achieve that level?
So I believe all the reported parameters are included in the model, but still in every model there is assumptions, right? Mm-hmm. And lattice Boltzmann has one limitation. Before to use it, you should be able to. So I'm using two-phase fluid, and two-phase fluid has a difference in density. In our case, let's say air and electrolyte, which has 1,000 times more, approximately. But there is a limitation in the lattice Boltzmann. When you simulate two fluids, it cannot go through 10 times more difference. So this is a limit. After 10 times difference, this becomes unstable. But this is the best case, at least across different models, which is reported in FEM, FVM, and LBM. So for now, what is the best scenario is 10 times. After 10 times in LBM or any other models, this becomes a bit unstable.
I see. Perfect. Thank you for your answer.
So there are more questions?
Yes.
Yeah.
So Abbos, here Michael Adamic asks, how much time do you recommend one should wait between electrolyte filling and formation, for example, for commercial CMMC cells?
Oh, this is quite a hard question.
Tough one.
Because there is too much parameters. like inside. So usually how they in companies how much electrolyte is decided, but basically calculating the possible porosity inside and putting the electrolyte right amount. So then you have a different cells with different porosities. Even this cell, I mean, it changes from producer to producer, and then what electrolyte you use, right? Because electrolyte like they have different viscosity and different contact angle. So it's a very hard question to answer. But maybe maybe here, like this study is the most closest one, I think. In the reality, is like last one I showed. This one, I think. Like you can see, this how electrolyte goes. Ultrasonic based visualization. So this here they are suggesting 34 hours. But it is only quantitative work. I mean, I saw it's like 34 hours here, and then here, like, oh, okay. So there is one more study showed around 22 hours, which I didn't show here. So it's very lot. So that's why it's very hard to understand. But I think this paper is good paper, and which is done by Jeff Dunn. So I think they're suggesting 34 hours in their case.
Fantastic. Here we have another question by Hannah Tirir Govena, who asks, you mentioned that electrolytes go into uncalendar electrodes fastly, and at the same time, you mentioned calendering of the electrodes will lead to smaller pore size. How can you relate this one?
Yeah, so when you have uncalendared electrodes, you have a bigger pore size and bigger porosity. Overall, it goes very fast. But then, while calendering goes on, pore size distribution becomes smaller, right? And then porosity decreases twice at least. So electrolyte goes slower. And then if you go too much, sometimes if you calendar too much, you always increase wetting degree. You have a risk of getting low wetting degree. So this is a conflict of interest bit, let's say.
Yeah. So with calendaring, you increase the tortuosity factor, right? So
yeah,
it's also about the way that the pores are interconnected with each other, right?
Exactly.
Good. And here we have another question by Mingse Han, who asks, what amount of trapped air in the cell/pores did you consider for your simulation?
So I calculated we have a geometrical data, right? And we calculated like how much air trapped is 100% sure by calculating clogged pores. So pores clogged by other particles, so no way electrolyte can go in. It was around 2, 3, 4%, depending on the calendering rate. And then I put electrolyte, and sometimes some air also bubble stayed within. And I think it could be also like, in our case, it was like 5%. When I showed you electrochemical results, it was 5-6%. But as well, you have to consider that one more assumption in my model is I consider carbon black domain as a particle. But in reality, it has microhomogeneity and micropores, which can hold also a bit of air inside trapped. So yeah, it's because of this limiting of the technique in the simulation. So we are neglecting micropores or nanopores inside the carbon black, which might hold some air as well.
Also, you have your swelling aspects, right?
Oh yeah, now we have a swelling model, so we see like how actually porosity changes after contacting with electrolyte, and it's quite fast. So yeah.
And here also another comment is the overall input is the overall contact angle is an input parameter for lattice-Boltzmann model, while in reality you may have different contact angles for carbon, for binder, and for active material, correct?
Oh yeah, sure, of course. Contact angle, overall contact angle, you just put drop and you will measure and it's input. Yeah. But inside the structure it might change and it doesn't take into account. And as Alejandro said, for example, for solid state electrolytes, when you have solid state which you put, and then after some time its viscosity changes, and this is very, very hard to take into account. And evaporation takes part, right? So which changes not only viscosity but density maybe. And so yes, this kind of assumptions behind the model very important to be considered.
Yeah. which is also, I think, a very nice challenge, right? For
Oh yeah,
physical
it's
simulations,
exciting.
eh?
It's very exciting actually to
Sorry,
solve this
right.
problem. Yes.
Okay, Fernando, do we have more questions?
No, we don't have more questions. Maybe a last one by myself. Abbos, do you think your simulations could be speed up in the future using GPUs, like, for instance, what was discussed by Sam Cooper before?
Yeah, actually, already LBM takes into account advantage of GPU. That's
Okay.
why it's fast. So more from computational side, GPUs increasing faster, right? So it will increase even faster, LBM. So difference between LBM method and other methods, I think it becomes even bigger.
I see. Fantastic. Well,
Yes.
thanks a lot, Abbos, and well,
Thank you very
Alejandro,
much.